Let's look at that problem with it's like the planar model of Sun, Earth, Moon system, and we will ignore the UFO. So there are multiple ways that you could do this. We're going to focus on the moon's velocity with respect to the sun, or the sun-centered inertial frame. Get the moon's velocity with respect to the sun-centered inertial frame. And in this world, the Earth is going around the sun in a circle with a constant angular velocity, phi dot, and the moon is going around the Earth with a constant angular velocity, theta dot. So we've got theta dot is constant, and phi dot is a constant. That simplifies things. It's another derivative we won't have to take. Now, if we translate this into the language of, there's like two different ways, right? There's the three-part velocity formula, equation 129. And then there's just the kind of transport theorem approach, which I would argue is the fastest. You do things in the fewest steps. So we ultimately want to get, let's put some frames in here. We need to define some frames because that makes life easier. Here's the Earth, and we've got the Earth-centered frame. I like using red for the inertial frame, kind of the main frame that you care about. And then I'll put the Earth, since the Earth is blue, mostly, seen from space, we'll call this we'll make these unit vectors blue. So that's ER, and then this direction is E phi. So we've got this E frame. E frame rotates with respect to the N frame, sun frame, with an angular velocity vector. Following the book's notation, this would be E with respect to N equals, well, the out of the screen direction is always the same. It's going to be either N3 or E3 or something else. So we'll just call that E3. So it's the angular rate, phi dot, and then the axis. That's going to be necessary for when we use the transport equation, and you got to take cross products. Okay. And that completes the right-handed coordinate system for this E frame, right? This E frame is a rotating frame. If you want to, let's call the Earth, call the Earth following the book's notation. The origin is O prime, over here is O. So the E frame has an origin O prime, and then if we were to write these things as like an X direction, a Y direction, a Z direction, we'd say ER, E phi, and E3, define that frame. Okay. And the moon, we're also going to give a frame to the moon, and maybe I'll make it green or something, because the moon is like cheese, and I don't know, maybe cheese is sometimes green. So this direction, we'll call it MR. It's pointing from the Earth to the moon. These are unit vectors that are just giving us directions. And then perpendicular to that is E as M theta. It increases in the direction that theta is increasing, if you want. Okay. And the M frame rotates with respect to the E frame, angular velocity, M with respect to E, and it's the angular rate, theta dot, E3. It's the same axis of rotation. And then if you wanted to say, well, how is the moon frame rotating with respect to that sun-centered inertial frame, or the N frame? It's just the sum of these two. So we'd say, well, it's how the moon frame rotates with respect to the Earth plus the Earth, the E frame rotates with respect to the N frame. So this is theta dot plus V dot E3. So far, so good. We haven't yet got into the meat. Now, this diagram is getting kind of complicated, but that's life. There's different ways to write what this velocity sun-centered inertial frame. This velocity, sometimes the book will write it as velocity of this. So here the moon is M, point M. It's a point with respect to the N frame. You can think of it that way. This is also, if we were to define the vector going from the sun to the moon, we'll just call that R. Right, and what is R? R is the vector from O to M. This is the derivative of R with respect to the N frame. And now we can write out, well, how would we write R? We can write R in terms of, I'm going to use maroon, going from O to the Earth, and then from the Earth to the moon. Going from O to Earth plus Earth to the moon. And given the unit vectors we have, I could write this as big. So from the O to the Earth, so from the sun to the Earth, the problem tells us that's a distance R, and it's in this ER direction that's attached to the E frame. Plus, what about from E to M? That is a distance little r. It's lost here. I think you can't even see it anymore. Little r in the direction from the Earth to the moon, which is MR. And with that in place, we can use, we'll use the transport theorem approach. I don't know if it needs to be capitalized. And I think this one takes the few steps, which may or may not be what you want. And you need to, yeah, we're just gonna go ahead and do it. Okay, so inertial derivative, or n, derivative with respect to the n frame of r, is what? Well, you just substitute in what we've got, r, er plus little r, mr. We can just plug that in right here, right now. And then some things we need to know, right? R dot is 0. We're talking about circular orbits. So big R is a constant and little r is a constant. So when I carry through this derivative using the product rule for a scalar times a vector, I'm not going to get any derivative of the scalar. So this would be, if I were to, I would have this times ER plus inertial derivative. Oh, I need to put a big N and R in front. Inertial derivative of ER, right? Plus derivative of little r in the MR direction, plus R derivative with respect to the N frame of MR. You might be saying, why am I not taking the derivative with respect to the N frame of a scalar? Because when you're taking the derivative of scalars, it does not matter what the frame is. So we can just drop that. And this is 0, and this is 0. So we're just left with these two terms. And notice what the main things are. It's the taking the derivative with respect to the N frame of some unit vectors. Okay. So what is the derivative? I'll call these out separately. Derivative of the ER direction would be, now I use the transport theorem. This is where this first step was just product rule, if you want, product rule. Now we use the transport theorem. So this would be, because it's a vector defined in the E frame, the frame that we use for the transport theorem over here on the right-hand side is the E frame. E with respect to n cross ER. Now, a unit vector that is fixed in the E frame does not change with respect to the E frame, so that's a 0. But then we're left with this part. And so this is, given what we have up here in the upper right-hand corner, the got phi dot E3 cross ER. And now I'm using the right-hand rule to evaluate that cross product. So E3, I kind of have to look at this screen up here. Look at that. Okay, E3 is up cross ER. My thumb is pointing in E phi. So, I evaluate that and I get E phi. So this is just phi dot E phi. It's kind of weird, right? This is the derivative of a unit vector. And we get that. So we would plug this in right here. And now we've got to evaluate this other one, derivative of the M frame. Now, if you're saying this does not seem like the fewest steps, but I'm doing it the long way. I could have instantly known, oh, well, these derivatives are 0, so I wouldn't have even written them. But it is the fewest steps, and it's the most systematic, and it works even if you have 20 frames that are all rotating, which happens a lot if you've got a complicated piece of equipment. So what about this? Okay, this is the inertial or derivative with respect to the n frame of an M frame unit vector, which means the natural frame on the right-hand side would be the M frame. Like, hold on, M frame? I don't know, I don't think we defined an M frame. Well, we do implicitly whenever we have a set of unit vectors. And you could have a frame, and this is a part that could be complicated. You could have directions that are changing without them being attached to any particular origin. So you might be wondering, why did I attach the E frame to the Earth, but I didn't attach the M frame to any, or I seem to have attached it to the Earth. Really, these M directions they're not attached to anything. You're like, oh my gosh, I don't get this at all. The only reason to think of the E frame as attached to an origin is to use the book's formula, equation 1.29, for that 3-part velocity formula, and then the 5-part acceleration formula. But technically, for the transport theorem, you don't need an origin for the frames. The frames are just the triad of unit vectors. And so plugging and chugging into here, omega m n cross mr. So I use the transport theorem with 2 different frames. And of course, here, the same thing applies as just above. The velocity, the derivative of an M frame unit vector with respect to the M frame is not changing, because as seen by that frame, that direction is not changing. But then what about here? Well, we wrote what M n is over this upper left-hand corner. So this would be theta dot plus phi dot E3 cross MR. E3 is just the direction coming out of the screen. So E3 cross MR, my thumb is pointing in the M theta direction. Well, I'll just do what I did above, which is kind of say M theta. All right, so this derivative is theta dot plus phi dot M theta. And I will plug that into here. All right, we are good to go. This, taking this down here, jumping down, the derivative, inertial derivative of the position of the moon, in other words, the inertial velocity of the moon, is r phi dot e phi plus little r theta dot plus phi dot m theta. And that's a perfectly legitimate expression. For consistency, though, I ask you to put everything into the E frame, which means we need to write this M theta unit vector in terms of the E frame. And if I were to plot, let me just schematically put the E frame. So this was ER, E phi, and then M R M theta, and this angle is theta, this angle is theta. We could work out what the unit vectors of the M frame are as written in the E frame, because it's just a rotation. So I'm going to do both. MR equals cosine theta ER plus sine theta E phi. M theta is negative sine theta ER plus cosine theta E phi. Okay, so I could substitute in there, and I'll get something, which now if I write it all out as a column vector, collecting terms and everything. So I'll pick up R, negative R, sine theta, theta dot plus phi dot. That's in that ER direction. And then for the other one, R cosine, little r cosine theta, theta dot plus phi dot, plus big R phi dot, and then 0. Okay, that was one way to do it. What if in here you had directly substituted in what MR is in terms of the E frame, so that you've written what this vector from the sun to the moon looks like completely in terms of E frame? You could do that. You could do that. That would be something else. Here. All right, so what if I used R equals, this is big R ER plus little r MR, and then I just substituted in MR written in terms of the E frame components. Then this vector would be big R plus little r cosine theta ER plus little r sine theta E phi. So now it's written completely in terms of the E frame. So now if I use the transport theorem, because all of the basis vectors are in the same frame, I would just be using the transport theorem for the E frame. Since all components in E frame, by all components, that just means I'm only using E frame basis vectors and only need, I don't know if this is simpler or not. I think it's kind of not. But we would take the derivative with respect to the N frame. And now on the right-hand side for the transport theorem, it's the E frame. E frame only. What is this? This would be omega E with respect to N cross R. And when I substitute everything in, well, theta does change with time. So I'm going to pick up a derivative there when I write this out. This is the derivative r plus little r cosine theta in the ER direction. And then let's just do both components first. So then a little r sine theta in the E phi direction. Then plus, and I'm just going to substitute in what I know for the E frame, how it rotates. This is phi dot E3 cross R plus R cosine theta ER plus R sine theta E phi. What do I pick up here? Maybe I'll move this down a little bit. Bit of a cheat. Okay. Because theta does change with time, I'm going to pick up this will be negative R theta dot sine theta. And what about here? R theta dot cosine theta. And then I could carry through these cross products. And at the end of the day, grouping terms, you're going to get the same thing. Okay. So this will also equal what I have up there once you group all the terms. And you can even check this. You're going to have to do something for the homework. So I'm just collecting all the terms I will get, when I evaluate these cross products and things. And then 0. So checks out. It's the same as above. Maybe you're bored at this point, but I think it's a worthwhile exercise to see that these are all giving the same thing if you apply stuff consistently. Okay. So what's the other approach? The book doesn't call this a 3-part velocity formula, but maybe this other approach is more intuitive to you. It works when you've got things moving on circular orbits, but it doesn't work otherwise. Yeah, before we get there, remember up here in this formula, this is the derivative of things as seen by the E frame. So all we have to do is plug in the components because we know that the unit vectors are not changing. And then the part that takes into account that things are rotating is just that, which we've just put here. So I just wrote it differently. All right. So another approach would be the 3-part velocity formula, which is equation 1.29 of at least the 4th edition of the book. In that case, let's draw the picture. We've got the origin. I'm just basically redrawing, but only including the key things. It talked about another frame, which it called B, but here it's the E frame. And if you were to write the vector from, here's the moon. And it called that vector rho. So in this case, rho is from O prime to M. So in terms of, yeah, we'll just do it this way. We would write that formula would say the velocity of m, the point m, with respect to the n frame is the velocity of the origin of this moving frame with respect to n plus the velocity of m with respect to the e frame, our moving frame, rotating and translating frame, plus omega e with respect to n cross rho. And then you have to think about what all of these are. So knowing that the Earth is moving on a circular orbit, maybe this will just be intuitive to you. Its velocity is what? This is big R phi dot in the e phi direction because it's moving on a circular orbit. And for this one, this is the circular orbit of the moon. So velocity of moon with respect to the E frame. And maybe this makes sense to you. This is R theta dot, and we'll conjure up that, M theta direction. That's a direction. It's this little unit vector direction, M theta. And then what about this cross product thing? Well, how do we write rho? Rho is R M R. So I feel like you still need to evaluate the cross product. So omega E n cross rho equals phi dot E3 cross R M R. So R phi dot, what is E3 cross MR? E3 cross MR, right-hand rule, my thumb is pointing in the M theta direction from before. So, okay, plug that in here. And I've got R theta M theta, or R phi dot M theta. Okay, collecting terms, what do I get? R phi dot E phi plus R, and this was a theta dot up here, R theta dot plus phi dot M theta. And so now we're back to a formula we had before, and if we were to write it in the E frame components completely, we will get the same thing. And so the cosmos holds together and math works. So that's nice. All right. So that was for just getting the inertial velocity. Okay, if you wanted to get the, maybe I'll put a check mark, say same as both above. So part of the transport theorem is you have some flexibility. And also there was some strange wording in the homework problem where I said, write your final answer in terms of E-frame components, because intermediate steps, it might be easier to use frames like the M frame, and then only at the very end, you'll substitute in, what is say, M theta in terms of E-frame directions. That's good. All right, what if you wanted the inertial acceleration? Oh. Inertial acceleration of moon? Well, again, the two main approaches would be the kind of use of the transport theorem, or the 5-part acceleration formula, which I think takes way more work. What would the transport theorem give you? I'll show you. Oh, this is a freebie here. Approach 1, right? We've already got what the first derivative of that position was, and we've written it up above a few times now. In its sort of simplest form that you get, you're sort of mixing the unit vectors from two different frames, but that's okay, as long as you write the final answer in terms of the E frame. Okay, so now if we wanted to get the acceleration is just the inertial derivative of this inertial derivative of that position, which means we could do everything we did before. We could either write the m unit vector here in terms of E frame, or just sort of go with what we've got. What if we just went with what we've got? Well, fortunately, these scalar expressions in front of the unit vectors, they do not change in time. They're constant, because we're saying theta dot is a constant and phi dot is a constant. So if you take their derivatives, you won't get anything. So the only thing that contributes something is, we could write it this way. So I'm skipping a step, but hopefully if you watch this, you'll kind of get it. I'm writing it that way. That's what you get from the first part. And then for the second part, r theta dot plus phi dot, the derivative with respect to the n frame of m phi. All right, and what is this? This would be, I can kind of jump to what it is. It's going to be omega, because this was written in the E frame, this is E with respect to n cross E phi. And what about this one? This is, because it's written in the M frame, this is M with respect to n cross m theta. And then what did we say this was? This is phi dot E phi. I know, E3. Three sounds like phi. E3 cross E phi. And over here was theta dot plus phi dot E3 cross m phi. And we gotta use the right-hand rule. What is E3 cross E phi? My thumb's pointing in the negative ER direction. So let's just say negative ER. And something similar is going to happen here. E3 cross m theta, thumbs pointing in negative MR. Okay, so if I just drop down here, I'll get, there'll be a negative, and I picked up a phi. So collecting everything, this is negative R phi dot squared in the ER direction, negative R theta dot plus phi dot squared MR direction. And that is like the most basic way to write it. Then I could substitute in, from what I know up above, of what the MR frame was. Remember what MR was? I don't. MR, written in the E frame components, is cosine theta ER plus sine theta E phi. So you could plug everything in and write this in terms of the E frame components. And I'll just sort of leave that to you. I don't think we need to belabor that. Now let's take a breath and rest. Maybe think about that. The other approach number 2, would be the 5-part acceleration formula, which may be more intuitive to you. I do not know. Yeah, because notice in here, there's no theta double dot or phi double dot, because the accelerations, we've got steadily rotating frames. So these are both 0, right? Since both 0. But we still have acceleration, right? And you would expect this, if we remember from earlier classes in physics, if you have something moving on a circular orbit, it's kind of weird. Like, I think, well, if something's moving in a circular orbit, the speed's steady, but it's changing direction. And because of that change of direction, there is a vector component to acceleration, and it's pointing inward. And that seems to be what we get. Inward towards the sun, and then for this other one, inward towards the Earth. And then you could write everything in terms of the E prime. Okay, the 5-part acceleration formula will give you the same thing. I've tried it, and it works. Here would be acceleration. I find this notation more cumbersome. Acceleration of moon with respect to the N frame would be the acceleration of our moving origin, which is attached to the Earth, with respect to the N frame, plus the acceleration of the moon as seen by the E frame, plus the angular acceleration of, because we're using the E frame as our kind of rotating frame, the E frame with respect to the N frame cross rho, plus the Coriolis, so omega E with respect to N cross this velocity. Like it's kind of nightmarish. Hold on, I want to get this one right. Looking in the book, this is, I guess I should tell you what formula this is. It's equation 1.35. We've just adapted it to the, instead of A and B frame, it's the N and the E frame. So that's the Coriolis. And then the last one is centrifugal acceleration. Nobody's gonna get mad if you say centripetal. I won't. But, that's why I like avoiding these, because this isn't a zoology class where we got to name terms. So just calling that Coriolis doesn't help me. Calling this centrifugal doesn't help me. And it does works out to the same thing. Of course, you don't have to do more than one approach. You just pick one. But you should get the same answer. Maybe to convince yourself, you'll try it. But all right. Okay, now we can take a deep breath. And before we go to Newton's laws, are there any questions that you want to bring up?
I have one question.
Yeah.
So if we were required to find the velocity and the acceleration, you would recommend using the transport theorem formula. But if we were just required to find the acceleration, would you say that the 5-part acceleration formula is a more direct way to solve that?
Not in general. I mean, if you have a good feeling for what each of these terms are in the acceleration formula, then yes. And it's, I guess, particularly easy for things moving on circular orbits. But in general, you'll have rotating bodies that are rotating unsteadily. So there'll be additional terms that show up. So I always think the transport theorem is the easier way to go. Also, there's always confusion about, well, what's the origin of my moving frame? And if you use the transport theorem, you don't have to worry about origins of moving frames. So you just think of the vectors, the unit vectors of the moving frames are just sort of directions. They're not attached to any origin. And that helps avoid some confusion. So I'm a big fan of the transport theorem. In fact, when we derived the 5-part acceleration formula, it was just naming some terms that you get from the transport theorem. So for example, for problem 3 of the homework, I wouldn't even know how to use the 5-part acceleration formula, to be honest. It's a good question. It makes a connection with what is often taught in earlier courses of dynamics or physics, that there's Coriolis, just blah, blah, blah. But the reason I'm harping on this transport theorem thing and dealing with rotating frames is because if you can get this right for how particles are moving, then you'll be able to get it right for rigid bodies. So that's why we've done 4 lectures talking about the transport theorem. there's a question, would I recommend using the transport theorem before or after transforming? I would use the transport theorem before transforming unit vectors. I would only transform at the very last step, kind of like I did here for the acceleration. It was a lot easier to just sort of plug in what I got from getting the acceleration written in terms of m and e unit vectors, and then keeping that going, and I get something particularly simple. And then at the very last step, I substituted in what is that m unit vector in terms of the e unit vectors. Good question. Okay, then. There will be lots of opportunities to do some stuff with the transport theorem.